So today, 5-7 wraps up our chapter, final section on a thing called the Trapezoidal Rule and Simpson's Rule. This is more like the first day than anything. The first day where we divided the shapes up and made rectangles. It's very much like that, but better. Here's the reason why this exists. There are some functions that have no antiderivatives. Okay, we started off the chapter doing integrals by cutting things up into pieces, and that was kind of a drag. Then we did integrals by, we had formulas that we wrote on our notes, and we just followed the formulas and plugged numbers in. And that was maybe less of a drag, but it still was a drag because you couldn't have like a list of every possible equation in the world. And eventually we figured out the most practical way to do these integrals was to just do the antiderivative and create a new formula and deal with that. But a cool fact of life is there are some functions that have no antiderivatives. And I don't mean you can't do them yet because you're young and doing calculus in a sense. You might not feel that young at doing calculus because you've been at this most of this school year. But you can take calculus for like years. Okay, it's like Calc 1, Calc 2, Calc 3, keep building, keep going, keep doing. Okay, but there are some functions that have no antiderivatives, not just for you young calculus people, but like they literally can't be done by anyone. Like they've been proven to be impossible. There is no like, do the antiderivative of this formula and it goes. I'm taking the book's word for it that these are two examples of things that not just you can't do the antiderivative, but like no one in the universe could. So Simpson Rule and Trapezoidal Rule is a thing you can kind of keep in your back pocket for that sort of a circumstance. So let's draw a picture and then we'll come back to what the rule actually is. So it's based on this picture draw motif where if we took this and split it up into fours for now, if we drew cappers on here, we were always doing rectangle cappers last time. If we did the cap from the left, I shorted myself some area that I needed. But if I did the cap from the left on this one, I included some area I didn't want, then we just hoped for the best. When we went from the right, the same kind of thing happened. We eventually decided that if we went up the middle and capped it at the middle, we'd include and exclude some things at the same time, and maybe that evened out even better. Somebody at some point decided, you know what, instead of rectangles, let's just connect from here to here with a straight line. And that's a trapezoid. Okay? A trapezoid has two parallel sides, and then the other two sides do whatever they want. But if we cap these off with straight line cappers, that one was almost perfect. You know, this we ended up short. This we ended up extra. We're still hoping to even that out over time, but you can sort of, when you look at that, you realize a trapezoid cap is a more accurate cap than a rectangle cap. If we had more time left in the period, I would like tease trapezoid area out of you, maybe not. Maybe it's in there, maybe it isn't. We did some trapezoid areas in geometry. But the way we would do the area of this trapezoid, you'd add the 5 and 11 and cut that in half. Okay? We would average these. They both count. But if we average them, we'd have the length of a thing through the middle that used to be called the median in geometry. Then you multiply by how tall that thing is, which is 2. If we look at these trapezoids now, they're stood on their end. Like you're probably, when you think trapezoid, you're probably thinking the shape oriented in this direction. Okay, but if we turn this sideways, if I wanted to do the area of this trapezoid, I would do this, and I would do that, averaged, to get the median. Then in trapezoid 2, I would do this again with that. When I did the next trapezoid, I would do this again with that. For the last trapezoid, I would do this again with that. So over time, all of these segments in the middle would get counted twice because they were the part of 2 trapezoids. The beginning line would only get counted once. The ending line would only get counted once because they were only the part of 1 trapezoid. So here's what the trapezoidal rule is going to do. The H represents how wide each piece is, and that will vary from problem to problem, but on my picture, that's my H. Each of these pieces would be the same width, they'd all be H. So width of the pieces. We'll divide by 2. The reason we're dividing by 2 is because the geometry of trapezoids requires that of us. And then we'd be adding up a bunch of sides. Okay, so like this 2 and this single trapezoid, that's like my H. Then these are like all the different lengths. Okay, we're going to add up the first side single counted, double the second one, double the third one, and so on and so forth, and so on and so forth, and double everybody in the middle because we get 2 of everything. But then we single count the last one, and that's the trapezoidal rule. Okay, it looks scarier than it is, okay, but this is just, we're getting these Y's. The Y's are coming to us either from a table, or maybe from a picture, or maybe from an equation we had to plug into. Who knows? We've had that happen to us before. We've gotten those heights from those sources before. So these are heights coming to us from our normal sources. This is a width that's largely under either our control or the book's control. If the book says make 4 pieces, well, the book controlled that. But if you were a professional doing this somewhere for some reason, you pick, oh, I'm willing to do 10 pieces, it'll be better. This is really important to me to be accurate. I need to do 20 pieces, like you control that. Or I don't really care, I'll do 2 pieces. It'll be quick, I'll check out with 2 pieces worth of stuff. But that's the concept of the trapezoidal rule. Question about that? Okay, Simpson's rule, I can't explain to you the geometry of Simpson's rule other than Simpson's rule uses a thing called parabolic arcs. I'm familiar with the idea of arcs. Arcs are like parts of circles. I'm familiar with parabolas, those are U-shapes, but I'm not familiar with how to do the area of parabolas and arcs. Okay, but his idea, the Simpson guy, sometimes he's a lot more modern than the other people working on these things, is instead of capping these off with straight lines, he found some way to cap these off with these like U-shaped parabola arc things, and I can't even specify exactly what that means. I'm honestly not sure. But the concept is, don't connect caps with straights, connect caps with curves, and then do geometry with that. And for whatever reason that I can't explain, the geometry of that, instead of cutting in half, the way trapezoids insisted that we were going to cut in half, for some reason the parabola geometry, you cut it in a third. Who knows? I don't know. And then instead of going single count and then all straight out double counts, which makes sense in the parabola picture I can draw you, for some reason this, or the trapezoid picture I can draw you, in parabola world you do start off single counting, but then you take turns between 4s and 2s and 4s and 2s, and you should end up with a 4 before we single count. So like if you're counting in from the, so you have to be careful about how many pieces you do for that to work out. Because if you're going to alternate, like you can't go 4-2, then back to single. You've got to go 4-2, 4-2, 4-2, a 4, and then a single. Like from outside in, we need singles, 4s, 2s. Like there's got to be a lonely 4 in the middle somewhere for that pattern to make sense. It's a little bit pickier. I can't explain the geometry, even though I could. You probably wouldn't care. But for whatever geometry, parabola, arc reason, it's divide by 3 and some quadruple counts instead of some single counts. These are potentially card worthy if you don't remember the pattern or trust yourself to remember the pattern. Maybe that's card worthy. This top one is the trapezoidal rule, the bottom one is the Simpson rule. If you kind of get the pattern while you do the homework, then maybe you don't even need to waste cards based on that. Maybe that's just like a big, long, scary looking formula that you don't actually need to write on your card. You make that call. But here's a problem. We'll do 2 of these, and hopefully we have time to do that. So this, if we do the integral from 1 to 2, and we want to split it up into 4 parts. Maybe it's a good idea, maybe it's an unnecessary idea to draw yourself a number line section just to see what you're looking at. So if we go from 1 to 2, and I split it into 4 parts, I'd split it in half, so I'm looking at 1.5. I'd split the halves in half, so I'm looking at 1.25 and 1.75. 4 parts is going to always require 5 numbers because it just does. Look at the picture, it's just the way that life goes. the first, if you just count the beginnings of 4 pieces, there's 4 numbers, but there's got to be an end to create like a 5th number for our 4 pieces. On this, I'm giving you an equation of x squared. So what we're going to have to do to all of these numbers is plug them into the equation where they're going to get squared and count some of them like multiple times as we go. So the trapezoid rule, I'd go 0.25 is how wide each space is. I would divide by 2. And then I'd plug in the 1 to get squared. Leaving a space on purpose, I need the 1.25 to get squared. Leaving a little space on purpose, I need the 1.5 to get squared. Little space on purpose, I need the 1.75 to get squared. And then I need the 2 to get squared. All of these numbers on my little graph, number line kind of thing, those are all going to get plugged into the formula, which in this case is squared. Some other problem we wouldn't square. We would do whatever the formula said to do. And then I left these little spaces because after we square, I need 2 of this one. I need 2 of this one. I need 2 of that one. And I just punch a bunch of buttons and out it's going to come. Question about the scheme on that? What that should turn out to be is 2.34375 seconds. Then the beauty of technology and the second entry button on the machine is when you do Simpson's Rule, the only real difference is it's over 3, and we want to get 4 of this one, and you want to get 4 of that one. So you just make those 3 little adjustments and hit the button again, and your calculator will say 2.3 repeats forever. You can see there's not much difference between the 2. Okay? If there was a huge difference between the 2, something wrong has happened. Okay? They should be usually pretty comparable. And then if they ask you to do the actual answer, which some questions do, by actual they mean do the antiderivative. Okay? The antiderivative of this would be 1/3 x cubed. That was my symbol from a few days back. That means it's time for me to plug in the 2 to get 8/3. Plug in the 1 to get 1/3. Subtract them. That's 7/3. 7/3 is actually identical to 2.3 repeat. Sometimes the Simpson's Rule absolutely spot on nails it. Simpson's Rule will be more accurate than the Trapezoid Rule. I don't have time to do the other one, so this is just sort of an incomplete video moment. So if we were doing this one, I'd have done my number line from 0 to 1, split it into 4 pieces, had 5 numbers. But when I plugged it into this formula, it was just going to be more work. 5 times this to the 4th, 5 times that to the 4th. Like this would have just gotten a little bit more expansive. But we'd have plugged those numbers in and basically done the same thing. Example 6, we'll just leave hanging for tomorrow because they'll cut us off for one day. So, one more Simpson Trapezoidal Rule example, just going back to where we left off. If you want to make a little sketch never hurts anything. So if we're going from 0 to 1 and we're trying to split it into 4 pieces, cut it in half and then again. So this would be halfway to a half is a quarter, halfway between those is 0.75. These are all numbers that we're going to have to plug in to the formula that we're given. So for Trapezoids Rule, we do how wide is each segment, 0.25, divided by 2, always. And then we're going to have to add up five things. We're going to count this double, and this double, because the Trapezoid Rule just says everything in the middle counts double, because if I drew you up all those triangles, every side would be part of a finish and a beginning of 2 different trapezoids. So I would need to go 5 times 0 to the 4th, that's a 0. 5 times 0.25 to a 4th, I'd rather use a calculator. So 5 times 0.25 to the 4th, I'll just calculate that later. 5 times 0.5 to the 4th, 5 times 0.5 to the 4th, I feel like it's probably a calculator moment, although that is 0.0625. 5 times 0.75 to the 4th, feels like a calculator moment, and I'm not going to do that one to show off. And if you don't want to punch all these buttons, if you're tempted to do 2 times 5, you could, but I wouldn't, and I'll tell you why in a second. If we plug the 1 in, 1 to the 4th is 1 times 5 is 5, but we're going to add up all that stuff and just see what it becomes. Question on that? Why I wouldn't do 2 times 5 punch in a 10 is because Simpson Rule was then harder to adapt. The Simpson Rule, you're going to do basically the same thing, but change this 2 to 3, change this 2 to 4, and change this 2 to a 4, and just let that roll. The 2 answers should be about the same, and if they are, that's confidence inspiring. I'm going to say trapezoid is 1.103515625, and for some reason in my notes I have a question mark, so maybe somebody disputed me on that and I'm doubting it for some reason, but I'm going to say that is my best idea for now. Simpson Rule I have is 1.00260. And I don't have a question mark on that on my notes, so I think I'm probably standing by that one. And then in a lot of the homework, they'll ask you to also find the actual answer. The actual answer means do the antiderivative. So x4 antiderivative would become x. Antiderivative of x4 becomes x. 5, and then we divide by that new power to the number in front, and that's just a 1. And then we do our little brackety friend. We were going from 0 to 1, which means plug in 1, 1 to the 5th is 1, put in 0, 0 to the 5th, 0, subtract those results, we get 1. That is exact. That's pretty doggone good. I never expect Simpson to be, I never expect trapezoid to be as close as Simpson. Sometimes it is, sometimes trapezoid gets lucky, but generally speaking, the trapezoid rule is not as good as the Simpson rule. Question about that? And then I wanted to do an example 6 that was based from a picture. So example 6 says, there's a town that wants to drain and fill a swamp. The swamp averages 5 feet deep, and they draw you a little map of this swamp to show like the different like lengths across this weird shaped swamp at different spots. And they want us to find the volume of the swamp. Well, to find a volume, foundationally first, you usually want to find an area. Okay? So if we look at this picture and we want to find the area, which of the rules is the more accurate rule generally? Simpson. So if I go to do Simpsons, I would do the horizontal spacing, which is 338 picture horizontal spacing. You'll feel silly if I tell you. 20? How do you know that?
It says horizontal spacing.
It says it where?
Oh.
Right under the picture. Right under the picture it says horizontal spacing 20. We always put that over. The Simpson is better. Over 3. And then we want to just add up a bunch of numbers. You'd want to add up 2 first. 146. Do we adapt that first one? No. Plus an adaptation for next.
4 times 123.
4 of the 122s, then
276.
2 of the 76s, then 4 of the 54s, then 2 40s, then 4 30s, and then a single 13. And that fit the pattern because they did the picture in a way that's helpful, but if you were ever in charge of this, you'd have to just make sure singles at the end, 4s inside, and then it took turns 2 4 2 4, and it does have to have a dead center position where you've got 4 or something. If you add that up, you'd get 8,100 for the area after you punched a bunch of buttons. Question about that. That's the area of the swarm. You need the volume of the swarm. So how would you translate an area into a volume? Here's a shape I can hold up. I could figure out the area of this doing circle stuff. If I wanted now to do a volume for the whole cylinder, how do we make that step? You multiply by the height. So what was the height of this swarm? On average.
Is that the 20?
No. Not in the picture, in the paragraph. 5. Average of 5 deep. So we would do this times 5. That's the volume. Is that okay? There's a homework question 27 that they go a little bit beyond that. You'd start with that, but then they tell you things. This is like a Peyton Blazevich kind of question here. They're putting fish into you're the fish and game warden of your township, but you're putting fish in this pond. So they tell you things like, once you get the volume, you're supposed to have 1 fish for every 1,000 cubic feet. So it's like not too ridiculous difficult to fish, but also not so fishy that it's like feeding the fish at Linesville at the spillway where it's just like a mound of fish. Then you want 25% of the fish to be remaining at the end of the season. So you have to figure out how many fish are in there, figure out how many fish that we're going to let the people catch. Then we're letting everybody catch 20 fish, and we're figuring out how many fishing licenses we're going to give out. It's somewhere around, I think, 1,000 fishing licenses, if I remember that answer right. But you'll just jump through some work problem hoops at the end. But the foundation of 27 is like getting the volume, and then you're going to have to like 7th grade story problem your way out of that. That's it for